Okay, in this podcast we're going to talk about Gibbs free energy and how Gibbs free energy will allow you to predict whether or not a reaction is spontaneous or thermodynamically favored. So in order to determine if a reaction is spontaneous, we need to consider the enthalpy, delta H, the entropy, delta S, and the temperature, and they all come together in Gibbs free energy. Okay, you probably will remember this from electrochem. So we can calculate the Gibbs free energy, which ultimately decides whether a reaction will go. And if you remember, delta G, if it's negative, means it's spontaneous. Okay. Might feel like I'm beating a dead horse, but I can't tell you how important it is, how many times people make mistakes. Entropy values are in joules. Enthalpy and Gibbs free energy are in kilojoules. And you need to be careful about making conversions. So if delta G equals delta H minus T delta S, and this is in kilojoules, and this is in kilojoules, and this is in joules, you got a problem. You got to do a conversion. Okay? All right. So there's lots of other ways to calculate Gibbs free energy, and the second way is just like we did with enthalpy and entropy. We just use the table of values. The key thing here is that the delta G for elements, just like for enthalpy, is 0. Okay? So if delta G is positive, the reaction is not thermodynamically favored. If it is negative, it is thermodynamically favored. And if it is 0, it means that you are at thermal equilibrium. Okay? And if you are at equilibrium, your K is also equal to 1. Hopefully you remember that. Alright. A third way we can determine the Gibbs free energy is to look at Hess's law of summation, right? And we'll do one of those, so it'll come right back to you. We can use the good old Ratlink equation that we also learned in thermochem, right? Not thermochem, but electrochem. And when we do that, we have to be careful of the R that we use, because the R is the energy R, and it is in joules. It has a joules component, so we need to make sure about doing conversions there, okay? Because delta G is kilojoules. We can also use the delta G is minus nth, right? Remember we did that? We had 96.485 coulombs, right? Minus NFE. Remember that 1 volt is 1 joule per coulomb. Okay. We'll do one of those. Alrighty, so let's take a look at some problems. So we are asked to calculate the free energy of this reaction to produce hydrogen peroxide from water and oxygen. And we are given delta G values. So all we have to do here is use the delta G of formation is going to be the delta G of the products minus the delta G of the reactants. And in this case we're given them in kilocalories per mole. So we're just going to take those values, and remember that the value for an element is 0, which is why oxygen's value is 0. And if I plug the numbers in and I do the calculations, I should get 59.0 kilocalories per mole. Okay. Let's take a look at another one. This one, we say we want to find the delta G of the reaction going from diamond to graphite. And I apologize, I have a little bit of an incompatibility issue when I import this. My arrows turned into these fancy A's, and just ignore that or change them to arrows. So here I have a reaction going from diamond in oxygen to make carbon dioxide, and here I have one from graphite in oxygen going to carbon dioxide. So we're going to use basically Hess's law, right? So we are, in order to do that, we have to rearrange the equations to get just what we want, right? So I can reverse the second reaction, and when I do that, I also have to change, I can cancel out everything that's common, and then I can, I have to reverse the charge over the sign of the energy, right? So, and then I can apply delta G is delta G of the products minus delta G of the reactants. I plug everything in, and I should come out with a tiny little negative 3 kilojoules per mole, which means it is spontaneous. Does not mean it's fast. It happens over thousands of years. Alright, so here's one that involves a lot of work. Here we got the A should be an arrow again. So the reaction above was carried out at 25C. We need to calculate delta H, delta S, and delta G using this data. Alright, so we have data here we can use to calculate delta H, data here we can use to calculate delta S, and then we can use the formula delta G equals delta H minus T delta S. Okay. Alright, so delta H, it's going to be my products minus my reactants, right? And oxygen would be 0. I plug in the numbers and I get minus 198 kilojoules. I do the same thing with delta S, and oxygen's value is not 0 in this case, so I've got to add it in. And when I do that, I get minus 187 joules per mole. Note that delta H is in kilojoules, delta S is in joules. Delta G is going to be delta H minus T delta S. I change the T to Kelvin. Now the thing that I do here is I just take that value in joules that I had here and I say times 10 to the minus third kilojoules. Okay? And when I do that, I end up with negative 142 kilojoules per mole. Alrighty. For this one, for the overall reaction, we want to find the equilibrium constant. So we need to find K. So the reaction that we have, the equation that we have that uses that is delta G is negative Rattling. So go ahead and try it, and then come back when you're done. Okay, so delta G is negative Rattling, and then I can also use delta G is minus delta H minus T delta S. Okay. So I wrote really small here, and I apologize, you probably can't see it, but I'm first calculating delta H using the table of values. Then I calculate delta S using the table of values. I calculate delta G using delta H equals minus T delta S. Once I have my delta G, I plug that into the Rattling equation and calculate my K. Alright. So when I did that, just to sum up, I ended up with a delta H of minus 165.2 or 1652 kilojoules per mole. My delta S was minus 0.53 joules per mole K. My delta G, when I plugged it into delta H minus T delta S, and I had to change my delta S units, right, by multiplying times 10 to the minus third. I plug them into the delta G equals negative Rattling, and this is probably the one area that people are most likely to make a mistake, is delta G is kilojoules, my R value is 8.314 joules per mole, joules per mole K, so I need to change that to kilojoules to make it work. Alrighty? And let me just make sure. Oh, the really disappointing thing is you may end up with getting a overflow error on your calculator because the K is enormous. So you should have ended up with K equals e to the about the 601. So K is about 10 to the 260th. Just some huge number. Okay, the important thing is that you can follow the steps. Alright, here's another one. We want to find the Gibbs equation can also be used to calculate the phase change temperature of a substance. During a phase change, the system is in equilibrium. So the delta G is going to be 0. Okay, So it's asking us to calculate the thermodynamic boiling point, which is the temperature, given the information below. So if it's boiling point, key word, boiling point tells us we are at equilibrium, right? We're in equilibrium, and delta G equals 0. So delta G equals delta H minus T delta S. I set delta G equal to 0. I rearrange the equation by adding T delta S to both sides, and I get this. I solve for T, which is delta H over delta S, and I get 44 kilojoules per mole. I've got to adjust the delta S by using the 10 to the minus 3 to get it to kilojoules, and I get a value of 370 K. That's my boiling temperature. Alright, here's, I think, the last one. Alright, for the reaction of CO2 plus oxygen, or I'm sorry, carbon monoxide plus oxygen to yield carbon dioxide, I have my delta G, and we want to calculate K, the equilibrium constant. I'm going to use RATLink again, and solve for log of K. And when I do that, remember my delta G is in kilojoules, my R is in joules, so I got to change it. Okay, this is moles K, and when I do that, I get 298 K. Oh, times 298 K, my bad. And then I multiply it out, I get K equals e to the 103, which is about 1.2 times 10 to the 45th. Alright, so time to summarize. If delta G is negative, the reaction is thermodynamically favored. If delta G is equal, I am at equilibrium, and my delta G is 0, and my E cell would also be 0, right, if I'm looking at electrochem. If delta G is positive, it is not thermodynamically favored, and my E cell ends up being negative. Okay. Couple of quick points. Common misconceptions. These will come up in probably multiple choice questions. But if one misconception is that if delta G is positive, greater than 0, which means it's not thermodynamically favored, that the process cannot occur. This is not true. You just need an external source of energy. Okay? So now consider the following. Number 1, an electrical current is applied to charge a battery. So this is be the case if you had a dead battery in your car, you needed a charge. You probably described the equilibrium condition for a battery as dead. It's not dead, it's just at equilibrium. Okay, so delta G is 0. You can recharge it. Okay. Light and photon absorption in the photosystems of a chloroplast causing photoionization during photosynthesis. These are sources of energy used to make that reaction go. You can couple a thermodynamically unfavored reaction with one that is favorable, and that's what's happening between ATP and ADP in biological systems. The other big misconception, this is part of why the College Board wanted us to shift from the term spontaneous to the term thermodynamically favored, is because they believe this misconception is really significant. And that is that if delta H is large and negative, that the process must proceed at a measurable, or you would even assume a fast rate. And this is absolutely not true. So kinetics is really separate from what's happening here with delta G. So if you have a high activation energy, like the reactions are held together really strongly, or you need the perfect collision. So you can have a negative process, a negative delta G, that is very, very slow. Okay? So delta G does not tell you anything about the speed of the reaction. Okay, we're going to stop right there.